Welcome to today's presentation on underload detection in the ACH580 and 580 Eclipse. Hello, your presenter today is Michael Morsfelder, and I am one of the HVAC Regional Application Engineers. I joined ABB in 2002, and I've been part of the VFD industry since 1981. My experience covers multiple aspects of the drive industry. In today's presentation, I'll discuss several aspects of underload protection or user load curve. Starting with the value of this feature, I'll identify various detection methods and problems associated with detection. I'll describe the preferred method for variable speed detection. And after covering detection in general, ACH580 detection will be described. Operation and setup will be discussed for both single load point and multiple load point detection. And last but not least, my discussion covers the Eclipse user load curve or underload detection and bypass. And to close this presentation, I'll review what we've learned. Why is this function relevant? Many building automation systems require underload detection in their job specs. And depending on the application, the feature is known as broken belt or proof of flow. But there are more practical reasons for underload detection: to verify airflow in a fan system, or to prove flow in the pump system. Now, this detection is intended to create an alert before a minor issue becomes a serious problem. So I have listed several examples of serious problems. Losing control of temperature in a hospital room, or damage to AC coils that are caused by a broken belt. That would be lack of airflow. Or damage to pump seals caused by closed isolation valves. That's an example of loss of flow. There are many proven methods to detect flow. The devices shown on the right illustrate types that are used to measure different system functions. Items like pitot tubes, pressure transducers, and other sensors are installed in HVAC systems, and they measure different functions like pressure, temperature, flow, and current. Then the device output is used by a building automation system to help determine if the system is working correctly. Current sensing relays use motor current to determine load, and due to the cost and the ease of installation, they are the prevailing choice for BAC contractors. Let's start with the drawing on the right. It represents a classic belt-driven fan with a motor starter circuit. When the contactor closes, the motor runs at full speed. A current sensing relay is shown in the blue box. That relay is monitoring the motor's current to determine load. The sensor is usually installed and adjusted by a building automation contractor, and the relay is set to trigger on a level higher than no load and less than full load. The pictures on the right represent two typical current sensing relays. I've added red lines to highlight the control terminals. And as we'll discover, These relays are not always the best choice, but they are the most prevalent. Traditional monitoring uses current to detect an underload. As mentioned before, current sensing relays are used on both full and variable speed applications. Graph on the right shows how current is affected as the speed increases. The orange line shows motor current with a belt off or a coupling disconnected, and the motor draws about 30% of full load amps. The blue line displays how current changes as the motor increases in both speed and load, and until the speed is above 66%, the difference is hardly detectable. The arrow on the far right shows a large difference between full load and no load. I've mentioned before that current sensing relays are not the best device for variable speed detection. Most HVAC applications today are variable speed. That means we need to learn more about current sensing detection. We just saw how full load and no load current differs at 100% speed. Another factor is that HVAC applications have a variable torque current profile. That means the current used by a fan or pump does not increase in a linear curve as the speed increases. In math terms, the load increases with the square of the speed, but in more practical terms, it means that detecting underload using current is more difficult than before, and here's why. The motor can operate from 0 to 100%, but a typical HVAC application has a practical operating range of 20 to 100%. So at speeds less than 66%, the change in current between loaded and unloaded is barely detectable, at least not with accuracy or repeatability. This graph provides a better detail for our load profiles. Percent speed is now shown as frequency, and the table on the left shows the data used to create the graph. An arrow shows the point where load and no load currents are measurably different. Our test has that separation starting at 38 Hertz. And we know that a motor speed in HVAC can be at 12 Hertz on a regular basis. So for this example, underload detection below 38 Hertz using current is not reliable. Measuring torque instead of current is a better method for underload detection. Motor torque is a measurement of work at a given speed. And you can see in the graph on the right, the torque curves for this application show better resolution than the previous curves for current. Our data table on the left shows two interesting observations. First, using torque, you can detect the difference between load profiles much earlier in the speed range at about 28 Hertz. By comparison, the same detection for current happens at 38 Hertz. Second, look at the low torque values for an unloaded motor. The torque starts low and drops off until the lowest point at about 42 Hertz. This reinforces the message that torque is the better choice for underload detection in variable speed applications. Setup of the underload protection is simple in the ACH580. After a successful startup, the first step is to view motor torque on the control panel. As with other 580 programming, navigation is simple. Under the main menu, select Diagnostics, then Drive Actual Values, and then select Motor Torque. Now, you can run the motor in the hand mode from 0 to 100%. You will find a specific speed that displays the lowest torque. Record both that speed and the percent torque value. Once recorded, then turn the drive off and navigate back to primary settings. The primary settings menu will make the underload setup fast and easy. The control panel still has primary settings displayed. From primary settings, select Advanced Functions and then select Underload Detection. Select the Enable box to activate underload detection. Our default selection for source signal is motor torque. Now with your recorded values for speed and torque, you can define load point 1 settings. For example, our data shows that point at 28 Hz and 9.8% min torque. I used 30 Hz for frequency point 1 and 8.5% for min load at point 1. In most HVAC applications, the min torque value for frequency load point 1 falls between 20 and 30 Hz. Our load point is 30 Hz. However, we still need to decide what to do with that information. The default action is to declare a warning and then a fault. And that detection includes a 20-second delay time to avoid nuisance trips. Of course, you can adjust the time to meet your on-site conditions. After the underload timer expires, a ULC fault and aux code 8001 are displayed on the control panel. The drive's fault or not fault relay will change state. With primary settings, a relay can be selected to announce this specific fault. Most building systems require this detection to be independent of other faults. To meet this need, the ACH580 activates a relay. Relay output 1 is the default setting as shown in the picture. Then, building automation can monitor relay output 1's status in several ways. They can hardwire relay output 1 to their controller. They can monitor the relay output 1 status using comms like BACnet, or they can read the user load curve status word. All previous discussions were focused on detection with only a single load point. Fans are a good example, yet there are applications that require more than just one load point. Centrifugal pumps are an example. No load conditions in a fan application are significantly different than no load conditions in a pump. And since most pumps are directly coupled, a loose or broken coupling is unlikely and certainly not the highest risk. A more likely scenario is that a pump loses flow, and that means detection will need 2 or more load points. Measuring torque at multiple points creates a better user profile. The graph on the right plots all 3 torque curves, including the no-flow curve, and the table on the left shows the data for these torque measurements. An important observation is that no-flow torque is higher than no-load torque, and that means a single load point is not enough to determine if the pump is working correctly. Without flow, water just circulates within the pump, creating excessive heat. If left unattended, this excessive heat will cause the seals to fail and the pumps to leak. The photo on the right shows a worst-case scenario. It was reported that both the input and output isolation valves were closed for a service procedure, but that status was unknown to the remote operator who turned the pump on. It continued to run until the water overheated and blew the pump apart. Shrapnel covered the site. So the message here is use multiple load point detection to create a user profile. Building a user load curve requires data. Looking at the graph, we can start with no load torque data displayed in orange. Full load torque data is shown in blue. And finally, no load torque data is the gray line. We measured full load torque by operating our pump in the hand mode. Torque values were recorded at 6 Hz intervals, and once this data was complete, the drive was stopped. To create a no-flow condition in our pump, the output isolation valve was closed. It was important to gather comparable data so the same frequency points were used. We ran the drive and pump in hand at 6 Hz intervals, and once we were complete, the drive was shut down and the isolation valve was opened. The resulting curve is displayed on the graph in gray, and the arrow on the far right shows the motors producing torque but no actual work. I know testing no flow by closing an isolation valve may not be 100% accurate, but the process of measuring torque provides details to make an accurate user load curve. A simplified rule of thumb is that no load is less than no flow, which is less than full load. Here is a more realistic scenario. A centrifugal pump supplies conditioned water to air handling units on all 6 floors in the building. The pump is in the basement, and the height of the water column creates some additional work for our pump. Under normal conditions, a building automation system is monitoring pressure, and when the temperature zones are satisfied, input valves to each air handling unit begin to close. Flow of conditioned water is reduced, and building automation responds by reducing the pump speed. Well, at some point on that speed curve, there is a potential for no flow. Without water flowing through the air handling units, the weight of the water column and the slow speed means that the pump may not be able to generate flow, and that means the pump is deadheaded. For an application with multiple data points, primary settings is still the correct starting place. For up to 2 load points, the screenshots display the same path as we used for a simpler application, such as a broken belt. The last screenshot shows using load point 2 selections. When 3 or more points are needed for a user load curve, navigate to parameters instead of primary settings. Group 37 offers an additional 3 load points for additional accuracy. After spending time on the ACH580, there is still the E Clipse bypass to discuss. The graph on the right was used much earlier in the presentation. However, bypass means that the motor only runs at full speed. And at 100% speed, current works fine for underload detection. We can see that full load current is measurably different than no load current. And as before, the no load current is about 30%. And by reviewing the variable speed curve, we can also see that the difference between full load and no load current only becomes detectable above 66% speed. So in bypass mode, that means that the underload trip point needs to be selected above no load current and less than full load current. Before I discuss the bypass underload or user load curve, here are some of the highlights of the Eclipse. We like to call this our smart bypass. At startup, all motor and overload data was entered into the ACH580 and stored. And the base drive talks to the bypass module, and all motor data is shared. There are several benefits with that structure. If the VFD was turned off, failed, or even removed, the Eclipse will still operate using the correct motor data. Another benefit, this design includes 2 independent CTs for current measurement. That means reliable and repeatable current measurements. Setup of the bypass underload detection is easy. And like the ACH580, no additional meters are needed. Setup for the Eclipse mimics underload selections in the base drive. On the bypass keypad, select parameter list, and the parameter groups are now displayed. Navigate to group 30 and select 3001 fault functions, and then select fault. Like the base drive, select a delay time and a fault level. With the underload detection enabled, we still need to program a relay that announces when an underload has been detected. Relay output 5 was used for this example, and the default selection is bypass and auto. The chart shows 2 possible selections for underload, and as the name implies, selecting bypass underload will change the relay only when the underload is detected in bypass. Another option is to choose system underload. This activates relay output 5 when either VFD or bypass underload is detected. And since underload conditions apply in either mode, system is the recommended selection, and monitoring can be hardwired or by a comms connection. Now that we've discussed underload detection in both the ACH580 and the 580 Eclipse, let's review what we've learned. Underload detection in both base drive and bypass has multiple benefits. These features eliminate the need for a separate current sensing relay. In drive mode, using torque provides a more accurate load profile. Multiple detection points, or user load curve, detects both underload and no flow. Typical of the ACH580, primary settings provides quick programming access. Underload detection for the drive or bypass or the system can be monitored by building automation by either hardwire or comms. Thank you for attending this presentation on underload detection in the ACH580 and 580 Eclipse.